Let's talk about states of matter now and their vapor pressures. So, first of all, what is a vapor versus a gas? A vapor means that at normal room temperature, that substance is a solid or a liquid. So, if you heat it up to the gaseous phase, then you call it a vapor. So, for example, water is a liquid. If I heat it up until it's steam, I would call it water vapor. So I wouldn't call it water gas. What a gas is a substance that are normally gases at room temperature. And if you look at the periodic table, uh, usually it's a red color that they use for the symbol of the element. All of those are gases. So chlorine, fluorine, oxygen, nitrogen, those are all gases at room temperature. Liquids vaporize or evaporate at the surface. And so this just happens normally. So in the picture down there at the bottom, the first one, right at the very surface, the molecules of the liquid are jostling each other and they're hitting each other and colliding, and then they are um, getting enough energy to break free of their intermolecular forces and to become a vapor particle or a gas particle. Typically, the molecules that are have the most kinetic energy or the warmer molecules, those are the ones that end up escaping or evaporating if it's water, or vaporizing if it's any other liquid. So it's called evaporative cooling, where the whole liquid will cool down once these hotter molecules at the surface will escape. So over time, if you had a glass of water in your kitchen, over time you would see the water level drop as the molecules at the surface are able to escape. Now, if I were able to put a lid on that cup of water, my water level would end up being the same. So here's this second example here. So as the water molecules become vapor molecules or gas particles, they will start getting more and more molecules, and so they will fill that space above the water, and they will start colliding with the surface of the liquid. So you'll get a situation where you'll have equal number of particles leaving as returning. And if you have a situation like this, it's called equilibrium. Those vapor particles above the surface of the liquid, I could take their pressure. This is my little pressure gauge. So I could have low pressure, I could have high pressure. If I had water, my vapor pressure above the liquid would be low. So vapor pressure is related to the strength of the intermolecular forces. And because I have hydrogen bonding in my water, then my vapor pressure would be low. So I wouldn't have as many water molecules above there, because the water is going to be able to keep a lot of the water just in the liquid phase because of that hydrogen bonding. However, if I had something else different, like say some acetone, and say this model was acetone, not water, I would want to draw more particles. And that's because acetone is held together in a liquid phase with just dipole-dipole forces. And so these are weaker than hydrogen bonding. And so as a result, I'm going to get more vapor above the liquid. And so I would describe its vapor pressure as being high. So again, high for acetone, and for water, it would be lower. So it has to do with the strength. So this next slide says that. So the stronger the intermolecular forces, then the lower the vapor pressure. The weaker the intermolecular forces, the higher the vapor pressure. And again, the vapor pressure is just those gas or vapor molecules above the liquid. They're slamming into the sides of the container, exerting a pressure. Now, we can also have a vapor pressure associated with solids, but they would be considerably less, because with a solid versus liquid, solid, their intermolecular forces would be a lot stronger just because of the fact they're a solid. And we already talked about dynamic equilibrium, when particles leave and return at the same rate. Let's talk about boiling point. So when you boil something, it's not the temperature that's making it boil, it's because of the pressure will be equal to the vapor pressure that's above it. We do use temperature to change that pressure of the liquid. So what boiling means is it means that the vapor pressure of my liquid is equal to the vapor pressure of the air around it, or the atmospheric pressure. So this is different than evaporation. So evaporation occurs only at the surface, but boiling happens throughout. So if you look at this diagram down here, you can see that throughout the liquid, the particles, their collisions are a lot more violent. Usually we use temperature to start increasing that vapor pressure of the liquid, and the collisions become more violent. They get more kinetic energy, and they'll slam into each other, and they're able to become a gas and be able to get away from their intermolecular forces, holding them together as a liquid. Every single substance has its own boiling point, so every substance has a different vapor pressure of its liquid to have it to be equal to the atmospheric pressure. So to boil something just in our kitchens, a pot of water, what we do is we put it on the stove and we start increasing the temperature. As we increase the temperature, we increase the vapor pressure of the liquid. And as that vapor pressure increases and increases and increases, eventually the vapor pressure of the liquid will equal the vapor pressure of the atmosphere. And then we say it's boiling, because there's nothing holding back those liquid particles from becoming a vapor or a gas. Melting point is also described the same way as the vapor pressure of a liquid being equal to the vapor pressure of a solid. So I could melt a cube of ice and it would melt at 0 degrees Celsius. That would not be the same for chocolate. So chocolate would melt at a higher temperature. So again, melting point would be when the vapor pressure of the solid, because that's the phase I'm in, being equal to the vapor pressure of the liquid. So boiling and liquid are all about pressure. So here's a diagram that shows vapor pressure of 4 liquids. First of all, let's find the normal boiling point for each. So remember, boiling point means that the vapor pressure of the liquid is equal to the vapor pressure of the atmosphere. And to find the normal boiling point, I need to look at standard pressure. So this dotted line going across here is going to tell me my normal boiling point for each of these substances. So I am using a standard pressure in this case of 101.3 kilopascals. Recall in our earlier goal that is equal to 1 atmospheric pressure, which is equal to 760 millimeters of mercury and 760 torr. So these are all your standard pressure. So what we're going to do is we are going to increase the temperature until the vapor pressure of the liquid is equal to this standard pressure. And then right when that line crosses the standard pressure, that's where your boiling point is. So my 4 boiling points here, the very, very first one, the line crosses about right here. Oh, let me change the color. Crosses about right here. And so that's about 56 degrees Celsius. Let's look at the next substance right here. So right before 80, so maybe 79 degrees. This next one is water. I know that one's 100, and we can read that. And the last one right here, this will boil at 5, so 105, 10, 15, so like 117, something like that. Okay, so again, these are the normal boiling points. Notice the overall trend that as the temperature increases, my vapor pressure increases. So this is why we heat our water on the stove to boil it, is what we're doing is we're manipulating the vapor pressure. All right, question number 2, which has the strongest intermolecular force? Well, it's going to be the one that we had to put the most energy into getting it to boil. And so the strongest one would be this last one. And so really it goes from weak to strong as we go across. And then number 3, find the boiling point if the pressure is decreased to 50 kilopascals. So one way to boil something would be to manipulate the pressure. So in class I did a demonstration where I boiled water that was warm. So and I boiled it on a plastic plate, and I did that by putting it into a vacuum chamber and pumping out some of the atmospheric air. So that lowered the atmospheric pressure, causing it to boil at a lower temperature. So if I lowered it to 50, all these boiling points would decrease. So for each of these substances, right where they cross that line. Okay, so go ahead and stop the video and answer these questions, and then we'll come back and answer them. Okay, we're back. So question number 1, what is the normal boiling point of ethanol? So ethanol is right here in the green. To find the normal boiling point, I have to find the atmospheric pressure. And the normal atmospheric pressure, this one here is measured in millimeters of mercury. So that'd be 760 torr, or excuse me, 760 millimeters of mercury. So just kind of drawing that line across, right where it crosses, I'm going to read this down. So the normal boiling point is, I'm going to say, like 77 degrees. So something like that. So anything close to that. Again, normal boiling point all has to do with standard pressure. So find the standard pressure and follow that across, and right where the line intersects with that vapor pressure line, that is the temperature at which it's going to boil. Number 2, which liquid has the strongest intermolecular force? It's going to be the one that has the vapor pressure is the highest with your highest temperature. So in this case, that would be heptane. So it's going to take a higher temperature to boil, so it must have the strongest intermolecular forces. And then number 3, if the temperature is raised, what happens to the pressure? There is a direct correlation. So as my pressure goes up, my temperature goes up.